Hi, in this video I will be teaching you transformations of quadratic functions, but today focusing on vertical stretches and compressions. So to do notes, we are going to be using this handout here. You can type this in your, you can print it or you can write this in your notebook. I just wanted to show you on the daily announcement where that's located. So if you'll go to your announcement, read through it. If you have not yet completed yesterday's assignment, you need to do so because today's lesson builds on it. You need to watch this video and either print the PDF that I'm using in the video. So when I say the print that is located at the bottom of this announcement, if you'll come down here where it says transformations of parabolas, if you were to click on that, you can then open it up and print it if you have capability. Okay, so I either recommend doing that or maybe getting some graph paper. If you've got graph paper available, you can always try to do it in your notes, but graph paper does make it a little easier. So just want to make you aware that that's where that is located. We are going to be doing some Delta Math assignments today. There are not a lot of problems. I think there are 14 total, and I'm going to be doing quite a few with you. So we'll be going to that in just a minute after I do the lesson. Do my student one so you can see what that looks like. So transformation day 1, please take care of that. That was due last night also, or tonight rather. I've got due tonight by midnight. So if you can take care of both of these today, that would be great. So you can see there's 14 problems. 10, 9, 2, transformation day 2, vertical stretches and compressions is what we'll be working on today. I'm going to minimize this. And you might want to also have Desmos up in case you want to verify anything before submitting an answer. But you do need to kind of really know this because, like I said, this concept is going to be one that you use in both Math 3 and 4 after this course. So transformations, again, transforming a function means to change it based off of its basic parent function, its most basic parent function. So again, parent function is y equals x squared. So if you practice like you were supposed to, then we did this yesterday. So it is very important to have in your own memory that the graph y equals x squared has a vertex at 0, 0. And from there we go out 1, up 1 on either side because 1 squared is 1 and negative 1 squared is also 1. And 2 squared is 4 and negative 2 squared is 4. So this is our y equals x squared function. Feel free at any time to pause the video. So a vertical stretch means you are stretching the y values by multiplying a number greater than 1 by the a value. So maybe I should use pen so it'll show it better. But stretch y is by multiplying a number greater than 1 by, I'm sorry, not the a value, but the x squared value. That's why I needed a pencil. So that number that we use to multiply is going to be the a value. So think about what we already know about y equals a times the quantity x minus h squared plus k. It means that you're going to have an a in front of the quantity x squared. So the first example I want to talk to you is what if you were asked to graph, so I'm going to switch up colors now, y equals 2x squared. So we already graphed x squared. What does it mean if we now put a 2 in front? Well, if you consider the table of y equals x squared, when y equals x squared, for those ordered pairs 0 to negative 2, negative 1, 0, 1, and 2, when we square those, we get 4, 1, 0, 1, and 4. But now what if I multiply by a 2? So if I now do y equals 2x squared, I'm taking these x squared values and now doubling them. So I'm doing this to illustrate what happens, but a table is not necessary, but it can help. So what are my new ordered pairs for the graph of 2x squared? 4 times 2 is 8, 1 times 2 is 2, 0, 2, and 8. So if you notice, my y values are now doubled. So they're going to double because I'm multiplying by 2. If you make a bet for $10 and you say, all right, I'll double that bet, now you're betting 20. So you're doubling the amount, okay? So what does that mean in terms of graphing? It means that now, instead of, think about our origin, our vertex rather, we still have the point 0, 0. But now, instead of going out 1, up 1, I'm going to go out 1, up 2. So out 1, up 2. Same for negative 1. Left 1, up 2. So now, for my values of 4, instead of going to 4, I go to 8. So I'm doubling my height. 2, 4, 5, 6, 7, 8. 2, 5, 6, 7, 8. So what happens is your graph actually is stretched upward. So think about if I were to take these two ends of my arrow and pull them. If I stretch them upward, my graph is going to get skinnier. So to kind of illustrate that, I pulled out a marshmallow. So if I were to take this, imagine this is our parabola. Okay, so I got my parabola. If I stretch it, what happens? I can see that it's getting pulled and it's going to get narrower, right? As I pull it, it's going to get narrower. So that's what happens for all a values greater than 1. In fact, if we were to do a little comparison, so now I'm going to go over here to Delta Math. If I type in x squared and we compare that to 2x squared versus 4, or it doesn't matter, 3x squared, as it gets larger and larger, what happens to the graphs? You can see that it goes inward, so they appear narrower. So it's kind of like taking those arrows, like I said, and stretching them upward. But unless there's a vertical or horizontal shift here, I mean, that origin is still going to remain our vertex. I mean, we can imagine what would happen. What if it was 100x squared? Wow, that's even skinnier. Look how skinny that is. It's very narrow, right? So the larger the a value gets, the more narrow the graph becomes. Okay? So again, how do I get the order pairs to graph this? Instead of going out 1, up 1, I'm just going to go out 1, up my a value. So let's write that down. From vertex, go out 1, up a. From vertex, go out 1, up a. And then really subsequently, we're just going to go out 2 and double. So we multiply the old y, these y's, by this a value. That's really it. All right. So that's a vertical stretch. What happens if we do a vertical stretch with a reflection? So if it's a vertical stretch again, my a value is greater than 1. And a reflection, my a value is negative. So what if I ask you to graph y equals negative 3x squared? So that would mean, think about what it means now, if I have my original parent function, which we should do it so much, we're like, oh, I can graph it super fast. Y equals x squared. If I want this to graph this one, first of all, we should recognize that if it's negative, it's going to open down. So that is an x-axis reflection. And then my A value is 3. So we don't say A is negative 3. Let's just consider we would say like the absolute value of the A value. So the absolute value of negative 3 is positive 3. So that means I'm going to triple my values. And remember here how I said y's double? Now y's will triple. So I'm going to write over here, y's will triple. But I'm going to open down, okay? So I'm going to do one thing at a time. Let's just talk about what it would look like if I tripled but did not flip it yet. So if I were to triple it, that means I would go out 1. Remember what I said. It's real easy. You're just going to go out 1 and then up A. So when I say out, that means left and right. So I'm going to go out 1, up A. So now I'm tripling that x value. It was 1. Now 1 times 3 is 3. Negative 1, if I triple it, after squaring it, I'm going to get a point at negative 1, 3. And that's really all you need is to recognize to move this point, okay? You're going to take these 2 points on either side of the vertex and move those. You'll see that when you do this in Desmos, the rest of the graph will move. You won't have to do multiple points. You only have to move 1 point to get it to go in the right spot. So if that's what y equals 3x looks like, 3x squared rather, then what will negative 3x squared? It just means we flip it down, right? We have an x-axis reflection. So we keep our vertex at 0, 0. Let me do this in purple now. Keep our vertex at 0, 0, but now this out 1, up 3 is going to be out 1, down 3. This right 1, up 3 is going to be right 1, down 3. And that's it. And just connect it to make a smooth parabola, going to the edge of the graph and making sure you put arrows on the end. So that's y equals negative 3x squared. Now, one of the things I'm going to ask you to do is like yesterday with the listing of transformations in your notebook, you definitely need to write down your transformations. So let's just talk about that real quick. So if I say list the transformations of this function, you would say it is a vertical, and you're allowed to abbreviate, stretch by a factor of 2. Why factor of? Factor is meaning that you're going to continually multiply by a value of 2. Over here, there are 2 transformations. The first one we did was a vertical stretch by a factor. Should have left a little more room there. By a factor of 3. It'll never be a negative. Just always make the factor that, because we're just going times 3 times 3 times 3. But then we also did an x-axis reflection. But remember, you can use your choice of phrases like I shared with you in the other video. You can say vertical reflection, reflected over the x-axis, or x-axis reflection. So these are your actual transformations. If I say list your transformations, this is what I'm talking about. Make a bulleted list of what happens. Now, eventually what we're going to be doing is combining vertical stretches and compressions and reflections with shifts, meaning I move my vertex. Okay? So now we're going to move on and talk about a vertical compression. So I want you to think about what it means if we were to vertically compress something. So I got another marshmallow here. So if I have a parabola, draw a parabola on my marshmallow. We are not eating these. And if I compress it, I want you to think about what that means. So to stretch it means to pull outward. To compress means to push inward from the top down. So that means, I want you to just think about what happens when I do this. What happens to my parabola as I press down here? See it spreading out? Isn't that cool? So it's spreading out. So that's what it means to compress vertically. To press down, and the result is that it spreads out. Well, think about what types of values might make it spread out. So we are going to, let's just add in here what that means. So we are going to compress y's by multiplying a number. So think about it. What might make our y's go down or become smaller? Well, to stretch means like you're multiplying values that make it larger, but to make it smaller, we actually want to divide. But that's another way of dividing is multiplying by a fraction. So we're going to compress by's by multiplying a number a between, and let me spread this out a little bit, between 0 and 1. So a, if it's between 0 and 1, will make it fatter. So I like to say fractions make it fatter. By the x squared value. By the x squared term, I should say. Okay, compress y's by multiplying a number between 0 and 1. So I'm just going to come down here and put between 0 and 1 by the x squared term. So in other words, if I give you y equals 1/2 x squared, because 1/2 is between 0 and 1, what is that going to do to our ordered pairs? So let's consider that table that we did a minute ago, where y values are x squared. If I square them again, I get 4, 1, 0, 1, and 4. But now I'm multiplying by a half. But think about it. If you multiply by a half, isn't that the same thing as dividing by 2? Yes, it is. So you can think of it that way. But we think multiplying by a half, though, because if, say, this was 2/3, then you wouldn't want to go divide by, I don't know, it just gets kind of funky. So we're going to continually think about multiplying by a half, which in your head, I want you to think, oh, that's the same thing as dividing by 2. So if I take all these x squared terms and now multiply by a half, let's look at what happens to our numbers. Half of 4 is 2. Half of 1 is a half, so I'm going to write that as a decimal. Half of 0 is still 0. Half of 1 is 1/2. I should have said -1 and -2, but once I square them, they turn positive. And then half of 4 is 2. So these are my new ordered pairs. So let's look at what happens. So we, again, remember our parent function. If I'm going too fast, I'm sorry. I just don't want you to have like an hour-long video. This is our y equals x squared. So now I'm going to graph these new ordered pairs. So -2, 2. Well, I'm going to start here actually at the origin. We still have the vertex 0, 0. Now we're going to go out 1, but we're only going to go up a half. So out 1, up a half. So see how I'm dividing my old y values in half? I'm going up half as much. Now I'm going to go out 2, up 2. Because I've got 2, 2, and -2, 2. So out 2, up 2. Out 2, up 2. Now when I connect those, look at what happens. Oh, that's definitely wider. See how that got wider like my marshmallow did? When I press down on this parabola, it spreads out and gets wider. That's a compression, okay? So that's exactly how you would do it. So you could do a table if it's helpful, but to be honest, if you just think, okay, I'm going to go up half as much as I normally would. So do you remember up here where I said if it was 2, you're going to go from your vertex out 1, up 2? So you're going to go out 1, up A. You're going to do the same thing here. You're going to go out 1, up A. So from the vertex, just like we did in the one above, so from our vertex, go out 1, up A. Now, it's helpful to have more than one point. It might be hard to draw a parabola and make it look like it's supposed to if you don't have this set of points that make it continue to go outward. So while you could just drag these points down, which is exactly what you're going to do in Desmos, then just remember yours, instead of going out 1, out 2, up 4, just cut that 4 in half and make it 2. In fact, we could go out 3. What's 3 squared? 9. But what's half of 9? 4.5. So out 3, up 4.5. So we could do that forever, right? But we don't need that many points to graph it. So that's how a vertical compression works. So I just wanted to make sure we did one also where you might have a negative. So let's do negative 1/3 x squared. So remembering our parent function is out 0, 0, out 1, up 1, out 2, up 4. That's super important to memorize. I'm going to do this in 2 stages. So the first thing I'm going to do is go out 1, up how much? The a value, 1/3. So that means if I were to take from 0 to 1 and divide that into thirds, I'm going to go out 1, up 1/3. Out 1, up 1/3. See how flat it's going to get? And then if I'm normally out 2, up 4, if I do 4 times 1/3, then I get 4/3, which if you were to put in that decimal, and that in your calculator to look at the decimal would be about technically it would be 1.3 repeating. So that means I go out 2, up 1/3. Out 2, up 1 1/3. And that's good enough there. We just want to make sure you show that width. So this would be y equals 1/3 x squared. Now with a negative, all I do is flip these points down. So I keep my vertex. This out 1, up 1/3. Instead, I'm going to go out 1, down 1/3. Instead of out 2, up 1 1/3, I'm going to go out 2, down 1 1/3. Now I'm going to connect. And this is the final graph that we want. So all we're doing is taking this 1/3. So I'm technically giving you multiple examples here, right? So that's going to be y equals negative 1/3 x squared. So again, you're flipping it and you're cutting those y values down 1/3 to 1/3, okay? All right, so back to listing these transformations. If I were to ask you to list these transformations, so I'm going to go over here to the left again, we would say there was only one thing. There was a change to the a value, so this was a vertical compression, so you can abbreviate it like so, by a factor of, and what is that factor? A. So that's all you would do. Vertical compression by a factor of 1/2. If you want to pause it and try the next one, you can do that. Vertical compression by a factor of 1/3 with a x-axis reflection or vertical reflection or reflect over the x-axis. Okay, so when I look at this, I see 2 things I have to describe. I have to describe what the negative does to the graph, and I have to describe what the 1/3 does. So think about the marshmallows if you're confused. And also remember this phrase. Fractions, and when I say fractions, I mean between 0 and 1. So I'm going to make that disclaimer. That means a value of a between 0 and 1. Fractions make it fatter. And you're going to notice that for all functions in math, that fractions between 0 and 1 will make the graphs fatter. All right. So there is a second page if you print this out, guys, where it says a greater than 1 will result in a vertical stretch by a factor of a. And remember, when I talk about a, I'm talking about y equals ax squared. That's the a value. Between 0 and 1 will result in a vertical compression by a factor of a. And a negative a will result in an x-axis reflection. There are other examples we could do. I just want to do at least one to show you how to combine all the things we've learned thus far. So if I give you 2 times the quantity x minus 1 squared minus 3, how in the world will we graph that? Well, first thing I notice is I see 1, 2, 3 things. So if I have to list transformations, I need 3 bullet points to list all 3. My recommendation is to always start with the vertex. Well, what is our vertex? Let's switch, keep. So our vertex is 1, negative 3. So all that means is from the origin, I'm going to go to the point 1, negative 3. But how would I describe that in terms of a transformation? If I go right 1, then I'm going to write right 1. And if I go down 3 to get to this vertex point, I'm going to put down 3. So I'm being really lenient here. I normally would say horizontal shift, right 3, vertical shift, down 3. But I'm letting you just shorthand it and say right 1 and down 3. But what does the 2 do? So remember, for all a values greater than 1, it's going to do what to our parabola? Stretch it. So that would be a vertical stretch by a factor of the a value, which is just 2. So graphing these is as simple as start with the vertex and then go out and up your a value. So this would be out 1, up a, which is 2. Out 1, up a. And that's really all you have to have. We usually like 5 points. So if you think about what we know about the parent function, it's normally out 1, up 1, put your points. Out 2, up 4, put points. But now it's going to be out 2, up what? So if we're normally out 2, up 4, that 4 needs to double, and 4 doubled makes 8. So that would be out 2, up 1, 2, 3, 4, 5, 6, 7, 8. Out 2, up 1, 2, 3, 4, 5, 6, 7, 8. So ideally, we would love for y'all to be able to graph these and understand these without ever having to use Desmos as a calculator. But can you use it to help you out? Of course. So you could always just go to Desmos and type it in. But I'm not going to do that right now. I'm sure this video is long enough. So we're going to conclude the written portion of those notes right there with that example. The only thing I could maybe add on to this is put a negative in front, which would just take this and flip it down. So instead of going out 1, up 2, we could go out 1, down 2 if that were a negative 2. Other than that, that's all the transformations you have to know. So therefore, after we've practiced this and then we practice Tuesday, you should be prepared for a test Wednesday. So this is extremely short, should be a very easy unit to do well in. So I am going to, just like yesterday, guys, with your notes, I want what's on the graph paper that I just did, but then I also want you to write the problems down and describe the transformations like we did yesterday to turn in as well. You're going to submit both. So let's go over here to our Desmos assignment for today on dilate functions. And for number 1, so you can call this Delta Math. This is our 10-9 transformations day 2. Always label your stuff, guys. I'm seeing when your teachers are saying that when you check, sometimes you're not labeling, but that makes it harder when you're going back to do your test. Okay, so make sure you're labeling your notes, okay, or any work that you put in your notebook. So number 1, I'm going to write this down. Oh, look at that. We already did it. Y equals 2x squared. So I'm writing that down, and I want you to tell me what your transformation is. Well, since we already did it, you can look at your notes, right? But let's talk about what this does. So I wanted to do it on paper, but also show you how do we do this on Delta Math. So if given this graph, notice how this has the parent function. You're always starting with the parent function y equals x squared. And your job, like yesterday, is to drag a point around to create this graph. So remember what I said, the vertex is going to stay the same unless it is shifted vertically and or horizontally. So that means all I need to do is take this point at 1, 1 and go out 1 and up the a value. Please remember that. It's not hard at all. That's my a value of 2. It means that instead of out 1, up 1, I'm going to go out 1, up 2. So all I have to do is click on this order pair at 1, 1 and drag it to right there at 1, 2. Doesn't that look just like it did on paper? In fact, if I were to graph it over here, graph 2x squared, if I wanted to verify a point, see that point is 1, 2. Is the point 1, 2 on my graph? I can click over here on Desmos. Yes, 1, 2. Okay, so I can verify some points that way as well. So I would submit my answer. Yes. And that's really all you're going to do. Here they're calling it a vertical dilation. We want you to make sure you just call it a vertical stretch or a vertical compression. So if I have 1/3 x squared, oh look, we already did that one too. If you look back at your notes, it's the one on the bottom left, but it's the one we did on the top that I did in pencil in the video. So it's a positive a value, so it's going to continue to open up. Instead of going out 1, up 1, we go out 1, up the a value, which is 1/3. Well, that's a lot smaller, right? So you can drag it down to here to about 1/3. One thing you can also do is think, well, if I have, which one's the easier to cut into 1/3? Is it easier to cut 4 into 1/3 or 9 into do 1/3 of 9? Well, if you think about it, 9 here is evenly divisible by 3. In fact, 1/3 of 9 is the same as 9 divided by 3. So that would mean instead of going out 3, up 9, I go out 3, up 1/3 of 9, which is definitely at 3. So I did 3, 3. So again, if you do this and you put it like really close, so think about where 1/3 would be, you're going to get it right. But certainly if the output value, either 4 or 9, is divisible by that 3, that makes it a little easier too. All right, so you're going to do a couple of those, and you're going to do, there's a 4. So think about what that means. It just means you go out 1, up 4 for your first point. So you just take this point, drag it up to 4. But I do have a couple in here that have like, there's a 3x squared. That should be easy. Out 1, up 3. All right, so let's talk about this one because there's a negative. So this would mean we go out 1, but instead of up 1/4, we're going to go down 1/4. Well, it might be hard to figure out where the fraction 1/4 is here, so which one of these would be easier? What is 1/4 of 4? In other words, 4 divided by 4 is 1. So that means it would be easier for me to move this point because 1/4 of 4 is 1. So that means I would go out, if it's normally out 2, up 4, so let me just start over. If it's out 2, up 4, 1/4 of 4 is 1. So I'm going to go out 2, down 1 because I have a negative, so it reflects down. So notice it's still out 1, down 1/4. It's just easier sometimes to think of using a different point, like that 4 times 1/4 was an integer, so that makes it a little easier. If you struggle with that sum and you still want to just go over here to Desmos, you're welcome to do so to make sure you drag it to the right point, because I agree, it would be a little tough to go, okay, where is 1/4 exactly? Right? Where's 1/4 compared to a half compared to 1/3? But what happens is, if you're even trying to do 1/4, that's definitely a half. But if I try to get closer to there, I don't want flat. That's a half, so you don't want that. So I would definitely do the 2 over 2 down 1, because it really is hard to make it do a fraction. Okay, but again, you can come over here and pick points if you like. So let me just remind you that you need to, in your notebook, each time you do this, go over and write what that transformation is. So number one, we would say vertical, what? Is a vertical stretch or vertical compression? It's a vertical stretch, y'all forgive my R, by a factor of 2. Okay? And then for the one I just did, this was number 7. So down here, if I go 2, 3, 4, 5, 6, 7. For 7, it was y equals negative 1/4 x squared. Then I've got 2 transformations. I have an x-axis reflection. And I have a vertical what? Fractions make it fatter. So that's a compression. Vertical compression by factor of 1/4. Do not put the negative in there with it. So I know I'm kind of going fast. I just changed the screen, but you can just go back and pause. All right, just want to make sure I give you all a heads up to help you out some. So what happens if I have this? What? Oh my goodness. So this is number 10, which is y equals 1/4. We just talked about what that does. What do I have going on here? Well, if I look at 10, this means I have a vertex change. So my vertex is now at switch keep 5, 0. So if you don't know where that 0 comes from, that's from the last unit, but also I explained that in yesterday's lesson. So I have 2 things going on. I have to describe what the 1/4 does, and I have to describe what this minus 5 does to the x. Well, remember, it's the opposite, and it happens on the x-axis. So how do we get to 5, 0 on a number line? Well, this vertex, all I got to do is shift it that way, right 5. So if that helps you, move it first and then go, okay, I went right 5. Oops. Wrong screen. Right 5. And then what does the 1/4 do? This would be a vertical, what? Fractions make it fatter. To make it fatter, I have to squeeze on it. So that's a vertical compression by a factor of 1/4. So this is what I'd want you to also take a picture of with your notes. It needs to be combined. I don't care if you have to take 3 pictures, 3 or 4 pictures. Submit all of them up to Canvas today through the announcements page. All right. So again, in announcements, we always have the link right here. Submit a picture of your notes, including answers as described in the video here. So you're just going to click there and submit. All right. Maybe one more just to help you out. Where am I at? That's the wrong window. So I didn't finish this, did I? So we shift right 5, and then that means I want to go out 1, up 1/4. But that also means 2, 4. I can make that 1/4 of 4, which is 1. So I'm just going to drag it down. Oop, nope. I'm going to drag it to 1, just not a negative. Bam. Now, if I'm like, did I do it right? Then I'm going to come over here to Desmos, type in my function, and make sure that these points match up, that I see the point 7, 1. Or, this one's going to be a decimal, certainly, but right there, those are going to be your integer order pairs, okay? So you let Desmos be your friend, drag it out. For those of you that forgot how to do that, all you have to do is take a tab, open up Desmos, click on Graphing Calculator. Like, say if this is maximized, you want to go up here and hit this button to minimize, and then take your Desmos tab and drag it to the side. That's all I do, okay? Then you can have side-by-side screens. Isn't that nice? All right, so let that guide your work. Contact us if you need help. At the bottom, I do have a couple where you're going to match the graph to, or match the equation to the function like we did in yesterday's, but these, now you can have a better idea of when these a values are not an understood 1, that it just, a value greater than 1 makes it narrower. So remember, like in this case, you'll identify the vertex. Here it is 1, negative 2. And if my vertex is 1, -2, I'm going to switch keep and look for -1, -2. So I'm going to look for the one that has -1, -2, but opens up. Nope, 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 nope. -1, -2, opens up. It's positive. There's your answer. So for number 14, there's your answer. All right. So good luck and let us know what you might need help with. Have a good week.